Hey everyone, and welcome back to the E³ Nexus Lab. This is the second episode of our Lulito series, where we're working our way through the battery technology crash course. In our last explainer, we covered the absolute basics from Chapter 1. Today, we're jumping right into Chapter 2 to get a handle on the key operational concepts. Ready to dive in?
So think of this chapter as the ultimate user manual for any battery you'll ever use. We're going to cover the specs, the fuel gauge. Then we'll get into voltage, current, and capacity. We'll also tackle the temperature challenge, look at how batteries age over time, and wrap it all up with how to choose the right battery for the job. Let's get started.
All right, first things first. Before we can talk about performance or how long a battery's going to last, we need to answer the most basic question of all. How much juice is left in the tank? Okay, so to measure that charge, you're going to come across two terms constantly. The first is state of charge, or SOC. That's pretty intuitive, right? It's basically your battery's fuel gauge. It tells you what percentage is left. Then there's its opposite, depth of discharge, or DOD. That just tells you how much you've used. They're really just two sides of the same coin. So if your state of charge is 80%, your depth of discharge is 20%. They always add up to 100%. Okay, so we know how to check the fuel gauge. Now let's talk about the engine, the actual controls, like voltage and current, that determine how your battery performs in the real world. So every single rechargeable battery has a voltage limit, a hard stop. But what if you just ignored it? What happens when you keep trying to cram more and more energy in past its limit? Well, that's what we call overcharge, and trust me, it's really bad news. See, that extra energy has to go somewhere, and it starts causing all these nasty, unwanted side reactions. Instead of just recharging, the battery starts to, self-destruct. In some batteries, it can literally start splitting water into hydrogen and oxygen gas. In others, it breaks down the electrolyte itself. This can lead to some seriously dangerous temperature spikes, and in the worst-case scenario, something called thermal runaway, and that is exactly as bad as it sounds. Now, when we're talking about how fast we charge or use a battery, we need a way to compare apples to apples, right? That's where this thing called the C rate comes in. It's just a standardized way to talk about current relative to a battery's capacity. Think of it this way. A 1 C rate is the current needed to fully charge or discharge a battery in exactly 1 hour. Simple as that. And the math is super straightforward. Let's say you've got a 1200 milliamp hour battery, and you're drawing 300 milliamps from it. You just divide the current, that's 300, by the capacity, which is 1200. What do you get? 0.25. So that means you're operating at a 0.25 C rate, or what some people call a C over 4 rate. Easy. So this whole C rate thing brings up a really interesting question. Is a battery kind of like a car? You know how if you slam your foot on the gas pedal, you burn through fuel way less efficiently than if you just drive steady? Does the same thing happen with a battery? Do you actually lose energy if you drain it too fast? The answer is a big, fat yes. It absolutely does. And this effect has a name. It's called Puckart's law. Now, a theoretically perfect battery would have what's called a Puchart coefficient of exactly 1.0. But just look at this table. See the old lead-acid batteries? Their coefficient can be as high as 1.4. That means they lose a ton of their usable capacity when you try to draw power quickly. But then look at modern lithium-ion. It's so much closer to that perfect 1.0 mark, which is a huge reason why it's so dominant today. All right, so it's not just about how you use a battery. Where you use it matters too. And the biggest environmental factor, by far, is temperature. Yeah, the cold can be brutal for batteries. Just look at this. When you drop the temperature from a nice room temp, say 20 degrees Celsius, all the way down to -20, the performance plummets. And you can see how different battery types handle it. A lead-acid battery? Yikes, it loses almost half its available energy. But again, look at lithium-ion. It definitely takes a hit, but it's way more resilient and holds on to a lot more of its charge. And this brings us to a really crucial trade-off. The cold, it's like a temporary penalty. The chemical reactions slow down, you get less performance, but once it warms up, the battery's basically fine. There's no permanent damage. Heat, though, that's another story. It might give you a little performance boost in the short term, but it's also speeding up all those nasty degradation reactions we talked about. Heat permanently damages your battery and shortens its lifespan. So cold is bad for today, but heat is bad forever. Okay, so we've talked about performance in a single cycle. But what about the bigger picture? Let's zoom out and look at the things that affect a battery's health over its entire life, from the moment it leaves the factory to the day it's ready for recycling. It turns out batteries follow a pretty classic pattern you see in a lot of engineered products.
It's called the bathtub curve, which is a great name for it. At the very beginning, you might get a few early failures. Those are usually due to tiny manufacturing defects. Then you hit this long, flat bottom of the tub. That's the battery's useful life, where failures are rare and random. But eventually, things just start to wear out. The internal parts degrade after thousands of charge cycles, and the failure rate starts to climb back up. That's the other side of the tub. And one of the biggest factors in aging is something called self-discharge. This is the energy a battery loses just sitting on a shelf doing nothing. And the difference between technologies here is absolutely staggering. Look at this. An old nickel-cadmium battery can lose 20% of its charge in a single month. Meanwhile, a modern lithium-ion cell, it loses maybe 2 or 3%. That is a game-changing difference.
Okay, I bet you've heard of this one, the memory effect, right? The old wisdom that you have to completely drain your battery before you charge it up again. Well, for the batteries in your phone and laptop today, that's pretty much a myth. It was a real thing for old nickel-cadmium batteries. What happened was, if you kept doing shallow charges, these tiny crystals could grow and reduce the battery's capacity. But even then, it wasn't really a memory. You could usually fix it just by doing one full discharge cycle.
You know, a much better indicator of a battery's real long-term health is its internal resistance. I love this analogy. Think of it like a battery's blood pressure. When it's brand new and healthy, the resistance is super low. It's like clean arteries. Energy flows right through. But as the battery gets older and goes through more and more cycles, that resistance starts to creep up. The arteries get clogged, and it becomes harder and harder for the battery to push out the power you're asking for. Okay, let's pull all of this together. We've talked about C-rate, temperature, cycle life, self-discharge, and when you look at all these factors, one thing becomes crystal clear. There is no single best battery. It just doesn't exist. And this table really says it all. This is the big takeaway. Choosing a battery is always about making a compromise. You want the highest energy density? Lithium-ion is your winner, but it's gonna cost you. Need something that can handle a crazy number of cycles? Nickel-cadmium is a workhorse. Need something cheap? Well, sealed lead acid is an option, but then you have to deal with that terrible self-discharge rate. See? It's all about balancing these trade-offs for whatever you're trying to build.
So the next time you plug in your phone, I wonder, will you be thinking about the C-rate of its fast charger? Or when you notice your phone dying faster in the cold, will you be thinking about its cycle life? It's pretty amazing, right? All these operational factors are what define how our favorite gadgets perform and how long they'll stick around. Wow, we covered a lot of ground today. I really hope this helped you understand what's really going on inside your batteries. If you enjoyed this episode, don't forget to subscribe to our channel so you don't miss the next part of our Lulito series from the E³ Nexus Lab. Thanks for joining us.